All right, good evening, everybody. Thanks for joining us tonight. I really appreciate it. My name's Dan Cornish. I'm a meteorologist here at the National Weather Service here in Gaylord. And we're going to talk tonight about winter weather. Specifically, we're going to talk about some science topics involving snowfall, how to measure snowfall, and then an outlook for this upcoming winter. So before I go ahead and hop right into it, I'll be taking pauses to look at the chat. Meteorologist Jeffrey Lutz is also going to be monitoring the chat and answering questions in there. So if you have any questions at any time, you can go ahead and put them in the comment section. But I will also be monitoring the comment section periodically to see if there's any questions in there that I could answer and maybe expand on a little bit. So with that, I'll go ahead and get started. So as I mentioned, the agenda, I'm going to first talk about what we do here at the National Weather Service in Gaylord. Just in case if there's, you guys out there not exactly sure all of what we do here at the office. So we'll go ahead and talk about that really quick first, and then we'll jump into the meat of the presentation. So we'll talk about system snow, we'll talk about lake effect snow, and we'll talk about lake enhanced snow. And then we'll go a little bit more in detail on factors that impact snowfall intensity. And then after that, we'll talk about measuring snowfall, and then we'll go into the 2021 winter outlook. So first off, National Weather Service in Gaylord. What exactly do we do here? So we are one of 122 National Weather Service forecast offices across the country. Specifically in Michigan, there are 4. So there is the Detroit office, there is the Grand Rapids office, there is the Gaylord office, which is us, and then there's also the office in Marquette. So us here, we are responsible for the northern lower peninsula and the eastern upper peninsula, and then we're also have forecast responsibilities for the adjacent nearshore waters. So basically extending out 5 miles into the Great Lakes outside of our area. And then we also cover the St. Mary's River system. So the diagram on the left, or the map on the left, that shows our forecast area outlined in the yellow. So if you are in any of the light blue counties, which basically extend from Manistee in the southwest to Gladwin County in the south, and then all the way up to the Mackinac Bridge, and then basically over to the Curtis area in the eastern upper peninsula, that is basically our forecast area. And so what we do for that area is we do a whole range of forecast products. So we do the days 1 through 7 forecast. If you go to weather.gov, that is the forecast that we do and that we work on every single day. We also do convective, winter, and marine headlines or warnings. So if you see things like severe thunderstorm warnings, tornado warnings, winter weather advisories, blizzard warnings, even like red flag warnings, frost freeze products, those all come from our office. So we issue those products for the forecast area that I went over previously. We also do the TAFs, or the airport forecasts for Manistee, Traverse City, Pellston, and Alpena airports. We do website and social media graphics. If you guys are joining us tonight on Facebook, then I'm sure you guys have seen our social media graphics before. But those are also posted online at weather.gov. And then we also do specialized forecast products and what we call decision support for our core partners. So the Coast Guard, emergency managers, and many others across the area, we will do specialized forecast products for them depending on what type of weather we're seeing and how it impacts them. We're able to relay weather information to them so then they can make decisions that fit their needs. And so with that, I'll go ahead and jump into the science topics. So specifically, we're going to start off with winter storms, or what we can describe as system snow. So this is, what we see is, what we describe as a system coming through the Great Lakes, and that could bring rain, snow, freezing rain, sleet. That's what we're going to discuss first. So the radar loop on the left showing the winter storm from April 13th through the 17th. Just to give you guys an image of kind of what we're talking about. So a prolonged winter storm event that dropped almost 2 feet of snow in parts of northern Michigan. You can see the observed snowfall amounts there on the right. 18 to 24 inches of snow, basically in a swath all the way from Grand Traverse Bay all the way over towards Rogers City. Some areas, right near 2 feet of snow, or 24 inches, right just north of Gaylord. northern Otsego County, and many other areas, above a foot, basically our entire forecast area. So systems can definitely bring some heavy snow. So what are some of the reasons why these systems can bring so much precipitation or so much snow? So we'll go over a diagram of what these systems look like. So when I say systems, basically talking about low pressure systems. So these systems have three main airstreams, or conveyor belts, you can think of it as. So we've got like a warm, moist conveyor belt. So that comes from south to north. So what that does is that transports warm, moist air from our south, near the Gulf of Mexico or areas to our south, and that brings that moisture northward into Michigan. And then second airstream is a cool, moist conveyor belt that will wrap around the system. So as you can see with the green arrow there, it wraps around the northern end of the system, and then a cold, dry conveyor belt. And so I'll emphasize that the warm, moist conveyor belts and the cool, moist conveyor belts, the orange arrows and the green, those are rising streams of air. So that's where we're seeing areas of ascent. And the cold, dry airstream, that is descending air or sinking air, or air that's falling closer to the Earth's surface. And that airstream, on the southern end of the system, that's going to be dry air. And so I should let off. In the center of the screen, you see the L. That is the center of the low pressure system. And then the red line with the semicircles extending from it, that is indicating a warm front. And then on the bottom of the L, you see a blue line with blue triangles. That indicates the position of a cold front. And so what that looks like as far as the precipitation goes is something like this. So if you were looking from top down on a radar view, this is what you would see. So a lot of times on the southern end of that warm front, you're going to see rain, even though some of those temperatures might be in the 50s and the 40s, even upper 30s. You're still going to see rain. Where a lot of times where you see the snowfall with these systems is on the northern end, or wrapping around the northern end of the systems. That's where that colder air is, and your better chances of seeing snow falling to Earth's surface. So as I mentioned, this is a top-down radar view. So this is looking at basically Mississippi Valley and the Great Plains. You can see Oklahoma and Texas in the bottom left there, and with the low-pressure system centered over Missouri there. And it's if we overlay the conveyor belts there, you can see how that precipitation is distributed around the system. You've got that warm, moist air being brought northward from the Gulf of Mexico and wrapping around the northern end of the system, where parts in the southeast United States, there in the bottom right of that image, so Mississippi, Alabama, they might even be seeing severe weather with this, or they're at least seeing thunderstorms where that warm, moist air is. But further north across parts of Missouri, Illinois, even Indiana with this system, that's likely where you're seeing your snowfall. And so with that, I'll take a quick break to see if there are any questions that I could answer further in the comments. All right, I'll go ahead and get into lake effect snow. So if you're watching, the news, you may be watching 9 and 10 or 7 and 4, or any meteorologist, you might hear them talk about cold air blowing across relatively warm waters of the Great Lakes. Will produce lake effect snow, something along those lines. Or if you read our forecast discussions, but why is that the case? That happens, but why does that happen? And two main contributors are instability and buoyancy. And so instability, when we're talking about instability, we're mainly focusing on rising air. So rising air, especially rising moist air, is what creates clouds and precipitation. So warm air rises relative to cold air because it has lower density. So you might have heard the term, or you might have heard the saying, warm air rises. That's the case because it's less dense than its surrounding air. And so for us as meteorologists, we're interested in areas of upward motion because this is where we get our interesting weather. So thunderstorms, snowfall, that's all generated by upward motion, rising air. And on the opposite end is downward motion. That's where we get our blue skies, calm weather. So as far as our impactful weather, we want to know where there's areas of upward or rising motion. And so any process that warms the lower atmosphere can create instability. And so adding moisture to this air also reduces its density. So if you've got warm air and it's moist, it's more likely to rise. And so warming the air or the layer of air from below while the air remains cool results in a difference in density. And so I go ahead and play the video on the bottom right here. This is a visual demonstration. So on the left, you have a jar of red water and a jar of blue water on top. And on the right, you have a jar of blue water and a jar of red water. And so red would be warm water and blue would be cold water. And as you can see, the demonstration on the left, where that red or that warmer water was on the bottom, that wants to rise, and that colder, more dense water in the blue jar wants to sink. And so you can see that those two jars mixed, and they're now purple. Whereas on the right, you have cold water, which is indicative of colder, dense air, and the jar on the top right, where you see red, that's warm, moist air that's signifying that, and you can see that those stay separated. So this is just a visual representation of rising and sinking air. And so now we'll get into the formation of lake effect precipitation. And so we can think of the Great Lakes as being giant burners that heat and moisten the air coming across them. So for a lot of our lake effect events, we see a cold air mass coming out of Wisconsin or Canada. So maybe you've got this cold air coming in out of Wisconsin and moving over the relatively warm waters of the Great Lakes. And so even though these waters might, especially during the winter, they might only be in the upper 30s, 40s, that's still cold water. You're not going to go, you're not going to jump in and swim in that water. It's still relatively warm because, that air coming across, it might be, in the 20s or maybe even in the teens. And so since it's colder than that water, that the cold air moving over the Great Lakes is going to pick up that heat, it's going to pick up that moisture. And when it does that, it's going to become unstable. And so that air is going to want to rise. And then eventually what happens is it rises to the point where you actually get cloud formation and precipitation formation. And so basically, the buoyant, moist air cools as it rises. It saturates, and that continued lifting leads to precipitation on the other end of the lake, which, lucky for us in northern Michigan, that falls on us, and that mostly falls in the form of lake effect snow. But even we can even get lake effect rain sometimes. If our air temperatures are in the mid upper 30s or maybe even the low 40s, especially early in the season. So late fall or late October, early November. That air, let's say it's, upper 30s, low 40s, but the Great Lakes are still in the 50s. We can still get that, instability over the lakes that can generate lake effect precipitation, but it will fall as rain. But, for the most part during the winter, when we got that cold air coming across, it's going to fall as lake effect snow. So, once it reaches us on the other side, that it runs out of its fuel source, so it's no longer over the Great Lakes. There's increased, friction. There's higher terrain across northern Michigan than over, obviously over the lake surface. And so that all helps force air upward and generate lake effect snow. But wait a second. So you might be thinking, not only does warm air rise, but we also talked about, cold air sinking. And so, in fact, that has to be that has to be the case. So how can we achieve both at the same time? And the answer to that is bands. So many times you'll hear us or other meteorologists talk about lake effect bands. And so lake effect bands occur where warm, moist air is ascending from the lakes, but in between bands, you get that cold air and that drier air descending to the surface from aloft. And this is just a satellite imagery of the Great Lakes, but you can see across parts of Lake Superior and like up here and even across northern Lake Michigan, you can see breaks in the clouds, and that's where that descending air is. And so the most common type of lake effect snow is multiple bands across northern Michigan. So there's a diagram shown below. So each individual snow band represents warm, moist air ascending from the low level. And that air is replaced by cold air aloft, which descends to the surface, and that's where you get that clearing between bands. Especially if you have stronger lake effect bands. As you can see in the diagram below, the orange arrows indicate where there's rising motion. So if you've got strong rising motion, that's going to help generate those stronger lake effect bands. But then there's also going to be the opposite occurring on the outsides, where you're going to have that downward motion. And many times, if you've lived in northern Michigan for a while, I'm sure you're familiar with it. You can actually see mostly sunny skies or partly sunny skies in between some of these lake effect bands, where even 10, 20 miles down the road, they're getting hit with inches of snow. So, definitely a unique part to northern Michigan. And so the way these lake effect bands orient themselves, or the position that they're oriented in, is due to the wind direction. So a lot of times you'll hear us talk about northwest winds or northwest lake effect. That's where the wind is coming from. So in this case, shown on the screen here, this is radar imagery. You've got northwest winds, and so how those bands are going to orient, they're going to orient parallel to the winds. So they're going to be with the winds. So I'm just going to draw some red lines. The was off. Yeah, so they orient themselves with the wind direction. So if you've got northwest winds, you're going to have lake effect bands oriented northwest to southeast. If you have north winds and you're looking at lake effect, the bands are going to be oriented straight north to south, and so on. A different type of lake effect, a little less common up here, is single bands. So we're talking about one dominant band of lake effect snow. And so this is the most common across the southern Great Lakes. So like Lake Erie and Lake Ontario, Buffalo, and areas especially just south of Buffalo are notorious for lake effect snow and heavy lake effect snow, where they've had events where a couple of feet of snow have fallen in the matter of a day or two, and that's because of single band lake effect. So this occurs when winds blow down the long axis of the narrower lake. So if you look at Lake Erie here, where the arrow's pointed, you can see if you have winds blowing from the western end of Lake Erie all the way down the axis of the lake, that air mass is picking up all that warm moist air, and it's rising, and then it finally gets to the opposite end of Lake Erie, and then it dumps it all there. So that's how areas just on the eastern end of Lake Erie can see those very impressive snowfall totals. And so the way this happens is, since the lake is really narrow, you can get the cold air on the other ends of the lake will push air out into the lake. Since that cold air is more dense, it'll push out over the waters, and that will create convergence. And basically, what we mean by convergence is that air is running into each other. And since it's running into each other, it can't those air masses can't go down into the lake. That air is forced to rise, and that's what's going to generate your single band lake effect snow. And since there's only one band, that band is typically a lot more intense than when that the warmth and that moisture is spread out between multiple bands. And so, like I said, there's events that where Buffalo can see a couple of feet of snow. And even during football season, they've had fans out there shoveling the Buffalo Bills stadium out. So you can get some pretty impressive lake effect with single bands. Like I said, for us here in northern Michigan, it's more rare, just because the way the wind is oriented northwest. You're not down the long axis of the lake. There's a lot of lake surface that the air mass is going across, so you're going to get multiple bands. You may see more single bands if you have prolonged northerly winds on the southern end of Lake Michigan. areas of Illinois, Indiana. But for the most part, it's most notorious, I should say, across Lakes Erie and Lake Ontario. So now we're going to cover lake enhanced snow. And when we talk about lake enhanced snow, it's kind of a mixture of both between system snow and lake effect snow. So snowfall from a passing weather system can be enhanced by the addition of the moisture from the Great Lakes. For example here, shown if we have a low pressure system that is moving from southern Michigan to our east here, you're going to have the northerly winds or the northeasterly winds to the north of that system. And so that's indicated by the purple arrows. And so if you have rising motion associated with the actual system, on top of the northeasterly winds picking up that the warmth, that moisture from Lake Huron, that's going to enhance the snowfall. So areas further inland may see an inch or two with something like this, but areas close to the lake shores may see several inches of snow because of that the enhancement. And so just to reiterate, it's not pure lake effect snow. It's just system snow. It's basically getting help from the Great Lake. And so another common example that we see is if we have a clipper system that basically comes from Alberta. If you've heard of an Alberta Clipper, it forms over Alberta, and then it goes east or east-southeast, and it crosses the Great Lakes. So if we have a low-pressure system moving across Lake Superior, we're going to have southwest winds across most of our area. And so those southwest winds, indicated by the blue arrows on the bottom of the L there, that can pick up warmth, moisture from northern Lake Michigan, and that can enhance snowfall totals across southern Mackinac County areas, like St. Ignace, Mackinac Bridge. Those areas can see enhanced snowfall totals compared to other areas that don't see that. So before I get into some factors that affect snowfall intensity, go ahead and see if there's any more comments that I could touch on. Yeah, Kyle, yep, that's exactly what I had in mind. The classic November 2014 lake effect event. There is, if anyone has time, that's definitely some good YouTube content. I believe there's a couple of YouTube videos that show, a video from that from tops of buildings in Buffalo where you can clearly see the convection off the lake, where it's picking up that moisture and then it's dumping it on the other end of the lake. If I remember correctly, there was, I want to say totals ended up being around 4, 5, 6 feet of snow, where even several miles, 10, 20, 30 miles away, they got very little snow, where that single band just set up over the same area for hours and hours and dumped just an impressive amount of snow. But that's exactly how you get those kinds of events, and why it'd be really, really rare to see events of that magnitude here in northern Michigan. But with that, I'll go ahead and get into some factors that affect snowfall intensity. So we've already talked a little bit about instability, but we're going to get into moisture content a little bit. We're going to talk about wind direction. I know we've already touched on it, but I'll go into detail about why it's so important, especially for lake effect snow. And then we'll get into temperature and how that affects snow growth. And we'll touch a little bit on snow ratios as well. And then we'll get into topography and how that affects snowfall amounts. And so when we're talking about instability, an important point is the depth of instability. So that's defined by how far up in the atmosphere the instability extends. And so we have deeper instability. That's going to allow for deeper convection or deeper clouds, and that's going to allow for greater snow growth. So just as an example, it can be difficult to get heavy lake effect snow if your unstable layer only extends, a few thousand feet, 2, 3, 4,000 feet in the vertical or up in the atmosphere. But heavy snow can still occur if moisture from a storm system exists above that. So that's touching back on what we discussed with lake enhanced snow. So even if your unstable layer only extends a little bit off the surface, if it's getting moisture help from a system that's moving through, that you can still get some pretty heavy snowfall totals. So as far as instability, the greater the difference between the air and the water temperature. You're reading a forecast discussion or even meteorologists, you hear the term delta T's. So it's basically the difference in temperature. What we're talking about is the difference between the air temperature and the difference between the water temperatures. And so if you have a greater difference between the two, you're going to have more instability, and that's going to allow for more intense snowfall. So this diagram just kind of shows that. So if we're talking about a water temperature of 10 degrees Celsius, on the left, if we only have a temperature difference of about 7 degrees Celsius, you're going to have, you're likely going to have lake effect clouds, but maybe it's not enough to generate lake effect snow. On the other hand, if your difference is, in the realm of, 13 degrees or 18 degrees, you're much more likely you're going to generate lake effect snow. And specifically, if you've got that higher difference, 18 degrees Celsius and 20 degrees Celsius, that can generate some pretty heavy lake effect snow. Don't let your eyes gloss over too much. So this is data from one of the weather balloons that we launched at our office. And so what it does is as it rises in the atmosphere, it takes readings of temperature, moisture, and we're able to get wind speeds from it. So this is just a plot of that. So think of, on the left, it shows height increasing. So as the balloon goes up, that's what it's measuring. So the red is showing the temperature, and the green is showing moisture. And so when the red and the greens are really close, that means you've got a really moist atmosphere. And you can see that the red is slanting from right to left. That's showing that the air is cooling, and cooling quite rapidly with height. And so when you have those lines close together, you have that moisture extending pretty far in the atmosphere. In this case, you have this instability extending almost up to 9,000 feet. This can help generate some heavy lake effect snow. And so I know I was just touching on that, but we'll get a little bit more into moisture. And so additional moisture provided by storm system can impact lake effect snow potential. And just in general, the more moisture you have, the better chances you can have of generating heavier precipitation, whether it's snowfall, thunderstorms, just in general. More moisture, the more intense precipitation can be. If you're mixing with moist air, or air that has higher relative humidity, condensation can occur more quickly. Your precipitation, your clouds are going to be enhanced. Like I've been saying, you can get your heavier precipitation here. Moist environments are often associated with large areas of rising air, which, like I mentioned at the beginning, we're interested in these areas. Where there's rising air, that's where we're going to see our interesting weather. On the other side, if we're mixing with drier air, your condensation is going to be slowed. So if you have drier air coming across the Great Lakes, it's going to take a little bit more time for that air to pick up that moisture from the Great Lakes and condense. Your precipitation is going to be diminished. Your cloud heights or your cloud depth probably isn't going to be as much. So moisture can often be a significant limiting factor. Just because we have northwest winds coming across the Great Lakes, if that air is really dry, we might not even see lake effect snow. Where on the other hand, if that's pretty moist air, then we're likely going to see lake effect snow. And so this is just another visual representation of that. So the clouds on the top or the bands on the top, it's showing a high RH or an environment that's more moist. So you're going to have clouds extending further up in the vertical. It's going to be more intense lake effect than the case shown on the bottom, where you have lower RH, or relative humidity. It's drier air. It's going to be a little bit more meager lake effect snow. Another a big influence on lake effect snow is wind, specifically wind direction. And so you want low level winds, so winds close to Earth's surface, to be of sufficient speed and a uniform wind direction. So when I say sufficient speed, you don't want really calm winds because you need that air to be moving over the Great Lakes. But for your heaviest snowfall, you don't want really strong wind. You'll still get lake effect snow, even in really strong winds, 20, 30 miles an hour if it's coming across the Great Lakes. But your heaviest snow or your highest totals will likely fall in between that wind speed. And so when we talk about fetch, what the fetch is it's the distance the air mass travels over a body of water. So the longer that distance is, or the bigger the lake, the bigger fetch you have. So like I was describing the Lake Erie and the Lake Ontario, those lake effect events. Down the long axis of those lakes, that's a really long fetch. So it's a long distance that air has to travel, and that's just a longer time that air mass gets to pick up all that heat and moisture from the Great Lakes. And the same thing can be said for Lake Superior. Lake Superior is obviously a huge lake, so when we get northwest winds coming across Lake Superior, that's picking up a lot of heat and a lot of moisture, even though Lake Superior's typically a little bit colder than the other Great Lakes. And so that's, we'll talk about our snowfall totals here, but, Marquette's area, the UP, they get even higher snowfall totals than we do. That's definitely a huge contributor to the lake effect snow totals that the Upper Peninsula sees. But that's also a reason why we do see the lake effect that we do here in northern Michigan. That air comes across Lake Superior, it picks up all the heat and moisture, dumps it on northern parts of the UP, but then it keeps traveling across and then over Lake Michigan. So that air is already pretty moist, and it still has that, like I said, it still has all that moisture. And so once it gets over Lake Michigan, it's already, ready to go again. It's picking up that moisture, that heat immediately, and it's ready to go for round 2 across northern Michigan. And so, like I've been saying, longer fetch lengths promote more precipitation. And then I talked about the upstream lake connection. So that would be an upstream lake connection for us. So Lake Superior, that cold air picks up all that moisture, and then eventually that cold air gets to here, and we're able to get some pretty intense lake effect snow. So snow ratios. What snow ratios are, it is the ratio of snow to the water content of that snow. So you may have heard snow ratios of 10 to 1. That's a very common snow ratio, or 8 to 1, 15 to 1, 20 to 1. What that means is, for the example of a 10 to 1 snowfall ratio, that is 10 inches of snow to 1 inch of liquid. Or you can think of it as, if I have 1 inch of liquid precipitation, that generates 10 inches of snow. And so 10 to 1 ratios are pretty common in system snow, like we talked about at the beginning. Snowfall that's directly associated with systems. When it gets pretty close to the freezing line, where you're starting to maybe mix in with rain, or maybe where you're even starting to mix with freezing rain or sleet, depending on the environment, those ratios will be lower. They'll likely be closer to 8 to 1, maybe even lower than that. Whereas in our lake effect events, you could see 15 to 1 ratios, 20 to 1 ratios, or even way higher than that. We've even had events where we can see 30, 40. If it's really fluffy, maybe we can even get to 50 to 1. So you can kind of think of it as getting a bigger bang for your buck. You have 1 inch of liquid, you have a 10 to 1 ratio, you're going to get 10 inches of snow. But if for some reason that was 20 to 1 ratios, then you'd get 20 inches of snow. So it just adds another layer of complexity. So it's not just how much liquid is falling, it's depending on the environment, how much snow are we going to get from that liquid that we're expecting. And so as temperatures aloft, so aloft meaning higher up in the atmosphere, so as temperatures higher up get colder, snowflakes become less dense. And so less dense snowflakes may accumulate more quickly. So for example, you see, your classic snowflake there in the top left, that have, a lot of the forks sticking out. So that could be less dense as they start to come together and intertwine. That won't be, there's going to be a lot of air between those individual flakes, and that's where you can get your fluffier snow. And so, as I alluded to, snowflake formation is pretty complicated. So if temperatures drop below 20 degrees Celsius, snowfall intensity and accumulation may actually drop off as the snowflake size gets much smaller. And so this diagram shows the complex nature of snowflake development, but we're not going to dig into the details of why this happens. Just want you to focus on the highlighted area there in the center. So this is displaying all different types of snowflakes that we see based on the temperature that they are forming in and basically how much moisture is there. And so if we have really moist air, and if we're looking at snowflakes forming in between the temperatures of around -12 to -18, this is what you'll hear referred to as the dendritic growth zone. And so this is where you're going to get your dendrites forming. So the big snowflake that you see in the top center of the screen, those are called dendrites. And so if you're looking for your highest snowfall ratios or your biggest bang for your buck, you're going to want dendrite formation. That's what's going to give you the most amount of snow for the liquid that you have. And so that is a lot of that is your fluffy snow. And so once again, showing a profile from one of our weather balloon launches, the dendritic growth zone is highlighted there in yellow. So won't dig too much into the details, but if you have a large or a deep layer of the atmosphere where that temperature extends through the dendritic growth zone, and it's moist, as you can see here, that's almost 11,000 feet of the atmosphere that's in that dendritic growth zone. That's going to be very favorable for the formation of those big flakes that you'd want to see in your higher snow. And so the last one that we'll touch on is topography. And so even a change of 100 feet in elevation can result in 8 to 12 inches of increase in annual snowfall. So a great example of that is areas that we see here in northern Michigan. So Antrim-Otsego County, our elevation's probably around 1,400 feet, mean sea level. If you're more familiar with areas across the UP, especially the Keweenaw Peninsula, which is here, you can see that there's also pretty strong elevation change. Same as here, the darker browns are higher elevation. And so where you get that that higher elevation, what happens is that cold moist air, or that that cold moist air that's going across the Great Lakes that's forming your lake effect snow, once it gets to the other end, once it interacts with land, if you have elevation change there, what that's going to do is that's just going to force that air up, and that's going to generate heavier snowfall in those areas. So like I mentioned, areas Keweenaw Peninsula, as far as snowfall totals go, that's just about some of the highest snowfall totals that you'll see outside of areas in the Rocky Mountains per se. That you could see well over 200 inches in the Keweenaw Peninsula on a good year. And so speaking of snowfall totals, this is a look at our average snowfall totals across our forecast area. And so not surprising after looking at the topographical map talking about lake effect snow, especially northwest lake effect snow, since the dominant wind direction in the winter, the most common is some sort of component of west and north. So whether it's north northwest, northwest, west northwest, it's very common, especially on the backside of passing systems. And so that is what helps generate the annual snowfall totals that you see here. So our highest totals across our area basically come just west of the Gaylord area. So basically, if you draw a line from basically Gaylord out towards Mansalona, somewhere in between there is where we likely see our heaviest snowfall totals. We don't have an official snowfall observer right in between that area where we have a really long period of record to compare climatology, but that's where we see our heaviest snowfall total. Areas near Traverse City see around 100 inches a year, and then areas on our eastern end, over near Alpena, see about 80 inches a year. And then once you start getting closer to Saginaw Bay, near the Gladwin area, Tawas, you start getting closer to 40, 50 inches a year. And that's because you're not really seeing that much lake effect snow down there. It's a lot more common to see northwest winds or northerly winds, like I mentioned, in the winter. So that's what's going to generate your lake effect snow, and that's why we see totals of I believe at our official Gaylord observation site, our annual snowfall totals just above 140 inches. So that's why we see those higher totals there, as opposed to some of our other areas where it's much more unlikely that we see lake effect snow with easterly winds or southeasterly winds. It can still happen. Some areas near West Branch, Aranac County last year got got a little over a foot of snow, I believe, with a pretty rare southeast wind lake effect event. But that's definitely not common. It can happen, but it's pretty rare. And so I'll touch a little bit on radar limitations. Might not be something that you would expect, but it's definitely important, or it's definitely an important factor to consider, especially if you monitor radar by yourself at home. So you're looking at the radar and you don't see anything, but it's snowing, especially across areas of eastern upper. There's a reason for it, and that's what I'm going to discuss here. So you see a diagram with our radar on the left, and it's shooting the radar beam from left to right across your screen. And so it is exaggerated for the point of demonstration here, but there's two reasons why the beam tilts upward. You can see it goes upward with height. So one reason is that Earth's curvature. It curves as it gets further away from the radar. So the radar beam is going to be further from Earth's surface the further away it gets from the radar. So that's one reason. And then two, our radar actually tilts slightly upward. So the lowest scan that it has is actually at a 0.5 degree tilt upward. And that's to avoid the radar beam bending down, or to avoid obstacles like trees or terrain. So those are the two reasons why the radar beam goes up with height as it gets further away from the radar. And so since that happens, that causes problems for us. So for example, we have storm A and then storm B, or we could say lake effect band A or lake effect band B. And so the lake effect band A is closer to the radar, and the beam's passing right through it. So the radar can see this lake effect band. But if we have a lake effect band going far enough away from the radar, like B in this case, the lowest tilt of the radar may be overshooting that completely. And so even though it's happening, the radar can't see it, or we're not getting any data from that. And so just as an example, here on the right, we have a vertical scale of your typical, or a summertime thunderstorm. I wouldn't necessarily say typical, but summertime thunderstorms can extend 40, 50,000 feet above the ground, which is pretty high up there. But your typical lake effect band is much smaller than that. Here we have one shown at about 10,000 feet, but that's a pretty intense lake effect band. Most lake effect bands are even smaller than this. So this is just a visual, so you can see the scale difference between lake effect snow band and typical thunderstorm. And so you're talking about the radar beam rising as it gets further away from the radar. This is a 3D view of reflectivity, so it almost has a bowl shape to it. So you can see as it gets further away from the center, which is our radar here in Gaylord, the further away you get from Gaylord, the higher up that radar beam is getting. And so I showed this radar loop earlier where you can see gaps. And so the question is, we have an arrow there in western Mackinac County, so that's probably right by the Curtis area, or right by the Big Manistee Lake, Southern Manistee Lake area. Is it snowing there? We don't see any reflectivity, but that doesn't necessarily mean that it's not snowing there. Same across other parts of the UP, especially near Sault Ste. Marie, Whitefish Point. It can be very difficult for our radar here in Gaylord to actually pick up lake effect snow that's occurring in those areas. So once again, if you're in those areas, or you're looking at those areas and nothing's showing on radar, that can be the reason why the lake effect bands just aren't high enough for our radar to see. And so the Marquette radar and our radar are about 60 to 100 miles away from those areas. So the lowest beam or the lowest elevation that the radar could see is right around 8 to 11,000 feet. So if those lake effect bands aren't extending that high in the atmosphere, the radar isn't picking them up. So satellite data can compensate from this. I showed visual satellite imagery. You can clearly see lake effect bands ongoing there, but it's also the reason why observations are so important. And so with that, we'll go ahead and get into proper snowfall measurement. But before I get into that, I'll see if there's any questions. Areas over near Manistee County can also experience those same problems, especially with shallower lake effect events. And it was also noted on the slide here on the bottom, but shallow convection where we have like drizzle, that can also be really hard to detect. Since it's not only if it's far from the radar, but since it's very light. If you're thinking about drizzle, very fine, very small water droplets compared to big flakes of snow. It's just harder for the radar to pick up, especially as you get further away. What kind of snow are we looking at for this weekend? So we're actually going to be looking at both. I'll actually get into a little bit of that later, but we're looking at a little bit of lake effect, especially across the UP Saturday morning into Saturday evening. But we're also looking at a system coming across the Great Lakes on Sunday and into Monday, where we're likely going to see system snow on the front end of that. So beginning in the Sunday morning time frame and lasting into Monday, but then we're also going to be looking at the chance for lake effect snow on the backside of that system. So as those northwest winds come in behind that system as it moves to our east, that's where we can see lake effect snow chances ramp up on Monday. And so with that, I'm going to go into a little bit of proper snowfall measurements and how you do it correctly, because we honestly love getting your guys' snowfall reports, whether it's on social media or if you call in pictures. It's all great. It really helps us for ground truth, to know exactly what's falling out there. So we enjoy it. So how do you do it properly? So we'll start off with definitions first. So when we talk about snowfall, emphasis on the fall part. Snowfall is measured to the nearest tenth of an inch. So, for example, 2.3 inches or 1.8 inches or 8.9 inches. So this is a measurement of snow that has fallen over a specific time period and then resets to 0 each day or at a specific time. So let's say that go out and measure snow that fell overnight. You measure your snow, and if you're measuring snowfall, wherever you're measuring, you wipe that area clean. And we'll get into the best sighting and details like that. But that measurement resets to 0, where snow depth is measured to the nearest whole inch. But that's what is considered snowpack. So basically, everything that has fallen over the course of the winter and has not melted. That's when we talk about snowpack and snow depth. So snow depth is the cumulative total of what has piled up on the ground all winter long. So let's say there's already been 10 inches of snow on the ground for a while, and then we get a system come through that drops 4 inches of snow. Your snowfall measurement would be 4 inches because that's the new snow that fell overnight, but your snow depth is going to be different. And so you may pick up 4 inches of new snowfall, but over the period of time, if that snow compacted, maybe some melted if there's warmer temperatures, it may only add 2 inches to your snow depth. So they're not exactly the same. So as I mentioned, that could be if you've got that dry lake effect snow where you have the high snow ratios of like 20 to 1, 30 to 1, that's going to settle over time. Wind may blow it around, making the measurements more complicated. So those are going to impact your snow depth. So the point being, they're separate measurements, and they need to be treated as such. So how exactly are we going to do it? So you're at home, you want to start measuring snow. First thing is you need to get a ruler, preferably in increments of tenths, and most normal rulers that you find at stores are like this. See the little lines in between, the 1 inch and 2 inch. Those are the tenths. So 2.2, 2.4. That's what you'll be looking at. So got to get a ruler and get out there and measure. So when we're talking about snowfall, we're going to measure from a snowboard or other light colored hard surface. Say a picnic table. That is a perfect example, or a perfect thing to use, especially a light colored one. Because if it's dark, if it's black or another dark color, and the sun hits it, that surface is going to stay artificially warm, and it might actually start melting your snow artificially. So we're going to try to prevent that as much as possible. So a snowboard, just a flat plastic, light-colored snowboard, or another similar hard surface if you don't have that. As far as where you should be measuring from, or the siting of your measurement, you're going to look for an area where the snowfall can settle in, or basically where there's a windbreak. You don't want to be measuring, right out in the middle of the open where there's nothing around it. That may be you may think that might be the best place to measure snow because there's nothing around it. Maybe nothing can artificially make the snowfall measurements higher. Say if there's roofs of buildings where snowfall can blow off. But if you measure out in the wide open, especially here in northern Michigan, even tonight, if you've been outside or hear the wind rocking, it can get pretty windy. And so if you've got, any sort of higher winds, that might start blowing snow off of your snowboard. So that'll be difficult to get an accurate measurement. So what you would like, especially here in northern Michigan, is you would like, maybe some trees, something blocking the wind, especially on the north side of where you're measuring. So the northwest side, the west side, the north side, since that's most commonly where your winds are going to be coming from. If you have, trees or something similar helping to block that wind in those directions, you're going to get a more accurate snowfall measurement because the snowfall is not going to be blowing all over the place. That's going to help prevent that. But like I said, you don't want it to be nestled in between buildings because that can cause inflated totals where you're getting snow that's not only falling on the board, but snow that's falling on the roof and then blowing back onto the board. So you're getting more snowfall on the board than what actually fell. And so when you do go to take your measurement, you want to make sure you're sticking your ruler straight up and down. It's not slanted one way or another. If you slant it, or if we call it slant sticking, you're going to get an artificially high snowfall measurement. So you want to make sure it's straight up and down. If it's been windy, you may have to measure in multiple places, and then use your best to get an average or a reliable measurement. And so when you do measure, you want to make sure that you get as close to eye level as possible. So you're looking straight at the ruler instead of down at it, because if you're looking down at it, it's you can be it'll be an inaccurate measurement. And so when we measure snow depth, like I said, think of snowpack. And so snow depth will combine both old and new snow. And this is measured to the nearest whole inch. So let's say snowfall, maybe your snowfall was 2.3 inches. But if there's no other snow on the ground, your snowfall depth is probably going to be 2 inches, or something similar to that. Again, you want to be cognizant of your sighting. You're probably going to have to measure, I should say it's best to measure in multiple places to make sure you're getting an inaccurate measurement. It may be 4 inches in one spot, 5 inches in another, maybe 5 inches in another place that you measure, and then you can average them out and get a pretty accurate measurement. Obviously, you don't want to measure in artificially high areas. Say you've been snow blowing, or other drifts or piles of snow. You don't want to stick the ruler right next to the house because there's probably a snow drift there or maybe drifting there. You want to make sure that where you're measuring is the most accurate area you could be measuring. So definitely don't want to be getting anything artificially high. And so, you're eager to report. You want to get out there and start measuring, but you don't know how to do it. So, let us know. There's a couple different ways to do it. You can call into the spotter line, but maybe the best way to do it is through Facebook, which you're already on, and through Twitter. We monitor both of our social media accounts 24/7. And so we're likely to see it, in a timely manner, especially if we've got, an event going on or a bigger event. We're going to be making sure that we're monitoring social media. And as I'm sure some of you have seen before, we may even, ask for your guys' reports. Like I said, it's very helpful to us to know how much snow is falling out there, and our forecast is there, but we like to, obviously know what's going on. So Facebook, Twitter. And sending us pictures, pictures worth 1,000 words. Sending us a picture with, the ruler in, making sure you've got a good sighting. That can be really helpful for us as well. Instead of, just saying that you got 3 inches, if we have a picture, with a, ruler showing 3 inches or, like 2.9 inches, something like that, that's the best thing that you can do as far as reporting. And then we also have Kokoroz. And so what is Kokoroz? Kokoroz is the Community Collaborative Rain, Hail, and Snow Network. And so it is a unique nonprofit, community-based observing network. And so it's comprised entirely of volunteers. And across the U.S., there's currently 20,000 volunteers and counting. And volunteers or Kokoroz observers can range, it can be any age. Current Kokoroz observers range from 7 years old all the way, to 80 plus. And so, in order to start observing, or if you want to become a Kokoroz observer, all you need is a 4-inch plastic standard rain gauge, a yardstick, internet access, and then most importantly, a desire to collect precipitation reports. And so this is just one example. This is actually from Texas, but the text is a little small, but you can see rainfall reports of 0.02, 0.03, 0.04, 0.01, but then you have one rainfall measurement of 7.12 inches. And this just goes to show that, especially in not very populated areas, having observers, especially, a Kokoroz observer, or if you guys relay or if you relay reports over social media, that could be extremely beneficial to know exactly what's going on. Because in this case, for May 6, 2008, really localized area of heavy rainfall fell, and where most areas didn't really see much, New Braunfels saw 7 inches of rain, and obviously 7 inches of rain is going to be very impactful, likely led to flash flooding. And so this is especially true with northern Michigan and lake effect snow. System snow is much more widespread across a much wider area than lake effect snow, because lake effect snow can be very localized. Gaylord might see 12 inches if it gets stuck under a heavy lake effect band, but areas to our southwest or even south, like Grayling or maybe Kalkaska, or areas to our north in Indian River, maybe those areas only saw 1 to 2 inches. So it's lake effect snow can be very localized, and if we have more observers out there, more snowfall reports, that can definitely help us know how much snow is falling in some of these lake effects. So if you have any further questions, any inquiries about it, www.kokoroz.org has all the information there in order to become an official Kokoroz observer. And so I should note, if you do become a Kokoroz observer, that is fantastic. And especially for snowfall events, rainfall, all of that, we monitor Kokoroz reports every single day for those events. So we will see the reports. And so, what about some predictions for this upcoming winter? And before I dig into the 2021 winter, I'll go ahead and see if there are any questions. And thank you, Jeff, for linking that right in the comments. You can take that link to kokoroz.org, and that will provide more information on becoming a Kokoroz observer. All right. I'll go ahead and get started with the 2021 winter. But first, before we dig into that, we'll go over El Nino and La Nina. It's something that's pretty common, or at least most people, or a lot of people have heard of El Nino or La Nina, or it's going to be a La Nina winter, or something along those lines. And so El Nino is something that's not really correlated to, or I should say, not correlated. It's not really involving northern Michigan. What it's looking at is sea surface temperatures across the Pacific. And specifically, when we're talking about El Nino is a warming of the central, eastern, tropical Pacific waters that occurs about every 2 to 7 years on average, where La Nina is the opposite of El Nino. So with La Nina, it's the cooling of these waters across the same region. It can last longer than El Nino, but the diagram on the right shows it. So, the reds, especially the darker red, that would indicate warmer waters across that area, and below it, you can see, lighter shades of blue or darker blue indicating cooler waters. And so this is just a time period of, or showing El Nino and La Nina years dating back all the way to 1982. So you can see how it can flip back and forth, a couple of years, of El Nino conditions, then La Nina, and it's fairly sporadic. But for this case, or I should say for 2021, we're looking at La Nina conditions, or expanding cooler waters, or cooler than normal waters across the Central Pacific. And so the animation on the left is showing the actual sea surface temperatures, where blue is indicating cooler waters, and the animation on the right is showing a very similar thing, but it's showing the sea surface temperature anomalies, or what we call departures from average, or how cool or how warm is it compared to average. And so the blues on the right are showing that it's cooler than normal waters, which what we're looking for if we're talking about La Nina conditions. And so here's a forecast from model predictions of El Nino and La Nina. This is from November, but it's showing that we're going to have La Nina conditions, extending through the winter, and then there's discrepancies as whether we go to a more neutral phase, once we come out of winter in the spring. But when we're talking about La Nina conditions in the winter, this is a typical La Nina pattern shown here on the screen. So you have your the jet stream is shown by the darker blue arrow, and then there's labeled areas of colder air, drier air, and wetter conditions. And so I should emphasize that this isn't what the pattern looks like all the time through the winter. But if you average it out, all the way from December, January, all the way through February, this is an average placement of where the jet stream is, and then also describing areas of wetter conditions and drier conditions. And so data taken from the past 70 years, looking at all La Nina events. This is the temperature departure from normal. So blues, especially the darker blues, that's much colder than average. And then where you see the darker reds, that's much warmer than average. So you can see as far as across Michigan and the Great Lakes, basically extending from Oklahoma up through Missouri, up into the Great Lakes, you really don't see any strong blues or strong reds. It's basically white, where it's average or maybe even slightly cooler. And so what that's showing is pretty much equal chances. There's going to be periods of colder than normal temperatures, going to be periods of warmer than normal temperatures. And so similarly, if we're looking at precipitation, you can see fairly similar signal, but you can see slightly leaning above average for precip goes. And so keep in mind, I'll emphasize later, when we're talking about precip in the winter, so December, January, and February, that doesn't necessarily mean snowfall. But looking at the past 70 years for La Nina events across the Great Lakes, you do see a little bit higher averages as far as snowfall go compared to normal. So what does that mean for this year? So this is the official winter outlook from the Climate Prediction Center. Like I said, this is valid from December through February, and it's showing pretty close to equal chances, or maybe slightly or leaning above, as far as better chances for above average temperatures through the winter. So it's really not a strong signal. And I'll emphasize, especially with La Nina in winters, you're likely going to see, somewhat of a roller coaster. There's going to be periods where you see, much warmer than average, much colder than average. But once you balance those out over the course of 3 months, it's really hard to tell whether we're going to see, above average temperatures over the course of the winter, or, colder than normal temperatures through the winter. But you can kind of see, relating back to what we discussed at the beginning of the presentation, that the separation between below average temperatures across, the Pacific Northwest, and then a lot of, the southern U.S. and the eastern U.S. Showing signals for above normal temperatures. The reason that is because that jet stream pattern that I mentioned, that's a favorable pattern for an active storm track across the Great Lakes. So our systems, the systems that bring snow that we talked about at the beginning, that's a pretty favorable pattern overall for, to bring systems through the Great Lakes. And well, that shows that we're, there's better chances for precipitation across the Great Lakes, as shown in the official outlook here for precipitation from December to February. Digging a little bit back to what I talked about with the systems, on the southern end of those systems, you have that warm, moist air, so it's not always going to fall as snow per se. So even though we may see above average precipitation, that might not necessarily mean we see above average snowfall across the Great Lakes. There's a stronger signal that we're going to see above average precipitation, but some of you may be thinking back to last winter where we had La Nina conditions, and snowfall across northern Michigan, across La Nina events, is highly variable. Some of our highest snowfall winters and some of our lowest snowfall winters, including for Gaylord last year, 2020, where we had our lowest snowfall ever for the period of record, which was around 75 inches through the entire winter, came from La Nina winters. So the actual snowfall can be highly variable. And part of the reason for that is, and especially last year where we saw as lowest snowfall totals as we did, is we really didn't get that much lake effect snow last year. So it wasn't, we just didn't, the storm track didn't line up, favorably to have those cold, northwest winds coming across the Great Lakes to give us, a lot of lake effect snow like we typically see. Like I said, we saw around 75 inches in Gaylord last year, and our average is right around 140. So we saw just about half of our season average of snowfall last year. Right now at the office, I believe we're a little bit above 30 inches so far this year. And then in town, I believe we're around 25 inches. I don't know the exact numbers off the top of my head, but we're already off to a decent start as far as snowfall is concerned. And so just summarizing winter 2021, overall, winter temperatures are going to be averaging near normal, but we're going to have periods of extremes, both warm and cold. That's not uncommon. That happens through every single season. But over the course of 3 months, when you average it all out, we're likely going to see temperatures average out near normal. We're going to have really cold spells, at times, and we could see temperatures even the next 10 days or so heading into Christmas week. For that, we could see above average temperatures. Actually, we're expecting above average temperature. So even snowfall on the ground now is already melted, but additional snowfall that we see this weekend, may mostly melt heading into Christmas if we get above average temperatures across the area. So that's likely going to happen over the course of the winter. Active winter weather is likely going to come with storms crossing the Great Lakes. There's going to be better chances for storm systems to cross the Great Lakes, and with these storm systems, we're going to get precipitation. So this is why there's better chances for above normal precipitation across northern Michigan. And then also, like I touched on, snowfall trends are pretty difficult to forecast in La Nina year. Historically, across northern Michigan, they're highly variable, and like I've been emphasizing, above average precipitation does not necessarily mean above average snowfall. And so, before I close out the winter talk, here are some local resources. So, if you go to weather.gov/Gaylord, that is our homepage. So, you'll see our current headlines. So, if we have any winter weather advisories out or anything like that, you'll see them on the homepage in the center. You'll also see our local 7-day forecasts, our hourly weather forecasts. You can see our forecast discussions where we discuss in depth the weather and the impacts that we're expecting over the next 7 days, as well as our graphics. So they'll be on the webpage, and our graphics will be on social media, so our Facebook and Twitter. So on the right is what you'll see when you go to our homepage. And then in the red box and the red circle there is where you can see your local forecast. So you can either click on the area of the map where you live, if you know where you live. So you, for example, you could click right on the Gaylord on the map, or you can type in your location. So if you type in Gaylord, Michigan, Rogers City, Michigan, Sault Ste. Marie, it will take you to a page that looks like this, where you'll see all the forecast information for the area that you typed in or that you clicked on. So they'll give you temperature, the weather conditions that we're expecting, whether it's sunny, mostly cloudy, snow, all that. It'll give you the details, and then also down there on the bottom you can see hourly weather forecast. If you click on that, it will bring you to another page that shows you more in detail, hour by hour, our forecast. So hourly temperatures, the hourly chance of precipitation, snowfall totals, as far as time of day when we're expecting them, details like that. So if you're interested in that, it's a great resource to have. And so with that, we'll be ending the winter talk. I'd just like to thank everyone once again for joining tonight. This is the first Facebook Live event that we did, so I hope you guys enjoyed it. Hope we got a lot of good information on snowfall this winter. Hope you enjoyed it. So with that, I'll look and see if there's any comments that I can expand on in the comment section. But this will wrap it up. So once again, thank you for joining. I hope you have a great night. Craig, as far as tours, at the current time with COVID, we are not having tours in the office, but we are optimistic that these will return sometime in the future. We're not sure when, but we can let everyone know when it's resume for the office. John, they so I just mentioned El Nino and La Nina, but other climate modes of variability is what we call them. But you mentioned the NAO, North Atlantic Oscillation. Those do play a part in the winter outlook or outlooks in general, as far as looking out several months in advance or a couple weeks in advance. Those also play a role, but just for this presentation, we just wanted to focus on El Nino and La Nina. Keep it. Didn't want to go too far into the weeds as far as the winter outlooks go. But if anyone's more interested in information like that, the Climate Prediction Center is they are the experts in seasonal forecast. So I definitely check out their page for more information on seasonal forecast. Once again, just like to say thank you for the kind words in the comments. We are looking to do more of these in the future. One of the main topics that we hope to do a Facebook Live for is our spring spotter talks. We're as of right now, we're planning on doing at least one over Facebook Live. This was just a test. So this was our first winter weather talk. We are going to be having another one next week where we register through GoToMeeting, but definitely wanted to give this a try, and we plan on doing more Facebook Live events like this in the future. But with that, I'll go ahead and end the Facebook Live. Once again, thank you so much, everyone, for joining us this evening. Hope you have a great night.